Good morning everybody and welcome to today's worked exam answer video. Today I'm having a look again at two multiple choice questions, both of which are covering content from the organic analysis A-level topic which is taught in year 12 ahead of the AS exams, but that I thought would be useful for year 13 students who are coming up to having a look at NMR, which is another spectroscopic technique that we use to help us identify what organic compounds might be. And a lot of the questions associated with NMR will also need us to use infrared spectroscopy data and potentially organic test data as well. So we might be told what substance we get a positive test with. So for example, there's one question I'm thinking about in my head and we are given the infrared spectrum like we are in this question here, and we can use that to identify the functional groups that are present in the compound. We're also then told that with acidified potassium dichromate solution we see a colour change from orange to green, which gives us some information about the functional group present as well, which is what question 14 is getting at. And then we're given the NMR data and it's using all of that data in conjunction to figure out what a compound is, its whole structure. So NMR is incredibly useful in its own right, particularly hydrogen NMR, but having additional information is very helpful, but sometimes you might be able to have two different structures that give the exact same pattern with hydrogen NMR, and that's where the chemical test might come in to help us then distinguish between those two structures. Again, the question I'm thinking of, there are two alcohols that we could draw which fit the NMR data. However, the information about the acidified potassium dichromate that we've added going from orange to green tells us that it has to be the primary or the secondary alcohol, not the tertiary one, for example. So I thought it would be useful to recap these ideas for those of you in year 13 who are going on to have a look at NMR, but I also know that this video will be helpful for those of you in year 12. I doubt any of you have got as far as organic analysis yet, but it obviously will be helpful in the fullness of time. So the first multiple choice question here, as I've said, it's showing us an infrared spectrum of an organic compound, and we have to, from the options provided, identify which compound could produce that spectrum there. So two ways we can approach this question. One, cover up the options, figure out what bonds are absorbing the infrared radiation at these particular wave numbers to work out what those peaks are referring to, and then figure out which of these compounds it could be from there. Or we could identify what all of the functional groups present in these four compounds are, and then match up those to the peaks that are present in the spectrum. Either way is absolutely fine. I'm going to first of all identify the functional groups, then I'm going to work through the peaks, so you can kind of see both methods in one. So, in ethanoic acid, it's carboxylic acid, we would expect to see a peak for a C double bond O and an OH acid peak. For 4-hydroxybutanone, the butanone part is a ketone, so again, C double bond O should be present. Hydroxy is the prefix we use for an alcohol group, so we'd expect to see an OH alcohol bond peak as well. Propan-1-ol, just an alcohol, so we'd only be expecting to see the OH alcohol peak and nothing else. And then for prop-2-ene-1-ol, we've still got an OH alcohol peak, but we would also expect to see a carbon-carbon double bond being represented by a peak as well. So in terms of these bonds, these functional groups that we're identifying, the position of those peaks is given to you on the data sheet in table A. So for example, if we have a C double bond O in our compound, we should see a peak between 1680 and 1750 centimetres to the -1. For an OH acid, we'd expect to see one between 2,500 and 3,000, and for the OH alcohol, it's 3,230 to 3,550 centimetres to the -1. The CC double bond is 1620 to 1680, and the thing that we need to know about the carbon-carbon double bond peak is that the transmittance remains quite high. It doesn't absorb a lot of the infrared radiation at that wave number, whereas these peaks come quite far down the y-axis, which is transmittance. So there is essentially maybe 5% of transmittance of that particular wave number of infrared radiation, which means it's being absorbed by that bond very well. The other thing that we need to think about with regards to the spectrum itself is that the fingerprint region, which is unique to every single organic compound, we're not really looking for peaks in the fingerprint region, goes from sort of the beginning of the spectrum on the right hand side all the way up to about 1,500 centimetres to the -1. So when we're identifying individual bonds and thus functional groups, we should not be looking sort of anywhere from 1,500 centimetres to the -1 to the right. And some of the peaks that are included in the table on the datasheet will be found in the fingerprint region. So a carbon-carbon single bond found in the fingerprint region, a carbon-oxygen single bond found in the fingerprint region. So I could have added a C to O bond, single bond, for all of these. Yep, for all of them. But firstly, if it's present in all of them, there would be no point, but secondly, we can't find it because it's in the fingerprint region. Same with the carbon-carbon single bond, that would be in all of these structures. So again, even if we could find it, then it would be a bit pointless. There is a peak in the non-fingerprint region area, which is also a little bit pointless, and that is that peak there, which is the peak for our carbon-hydrogen bonds. Again, that's going to be present in all of those 4 options and nearly every single organic compound, unless we have substituted the hydrogens for halogens. There may be others that don't have a carbon-hydrogen bond, but I would say the vast majority will. So again, that's not a very helpful peak for us at all. To be honest, the 4 peaks that I would suggest that you are happy with and can identify are the 4 that are included in these 4 options. These are the 4 most common peaks. There will be others that may come up once or twice. There's others that I've never seen come up in a question, but these ones will. Particularly C double bond O, particularly the OH acid, particularly the OH alcohol. CC less so, but still it's one of the 4 that I would be looking for. And then all we would be doing is having a look at where the peaks line up with the x-axis and those wave numbers. So that light blue peak there is just over the 1,700 centimetres to the -1 mark. So that is going to be a C double bond O, because the C double bond O peak is found between 1680 and 1750 centimetres to the -1. And as soon as we know that we have a C double bond O peak, we can then rule out C and we can rule out D, because neither of those alcohols have a C double bond O in them. So that crosses 2 of the options out. Then we're distinguishing between, do we have an OH acid peak or do we have an OH alcohol peak to give us either ethanoic acid or 4-hydroxybutanone. Now, as I've said, that peak there is our CH bonds, so not looking at that. So we're then looking at this one here, which is quite a broad peak, which means that it's not nice and thin and slithery like the C double bond O. It's quite wide, and that falls in the region of sort of 3,200 to 3,500, and that very nicely matches up with our OH alcohol peak, which we find between 3 to 30 and 3, 5, 50 centimetres to the -1. And at that point, we can then say it's not going to be A, because we don't have the OH acid peak, which would be between 2,500 and 3,000, which some students would confuse with this peak here. That, if we had an OH acid peak, would kind of merge onto the side of it. So you'd get like a peak, and then you'd have this little weird two-pronged peak there. We don't have a big OH acid peak there, so that rules out ethanoic acid, and obviously therefore means that my answer here is B. We've got 2-hydroxybutanone. Any questions about that? Any questions about any other infrared examples? Please do let me know. I think the more meticulous and conscientious you are, the harder you find infrared spectroscopy because you overthink it. I've been there myself. I totally understand why, but try be a little bit more liberal if you can, and hopefully so far there's not been any peaks that they've given us in spectra, where it's a bit ambiguous. So you should be able to figure out what bonds we've got, and then that can obviously help when it comes to an NMR question, because in that case we would know, somewhere in my compound I need there to be a C double bond O, somewhere in my compound I need there to be an OH alcohol. Now we don't know how many C double bond O's or how many OH alcohols, but it gives us a good starting point, and this is where using lots of different information in combination is the most effective thing we can do. And as I said earlier, some of that information might be chemical test data. So in this table here in question 14, we can see that we've got 3 reagents being added separately to 4 organic compounds. So the first thing that I might suggest that we do here is identify what all of these reagents would be testing for. So Tollens reagent is probably the one that people remember the easiest. So Tollens reagent is how we would test for the presence of an aldehyde. So we'd need a C double bond O on the end of our chain there. So that's all that Tollens reagent would show the presence of. It doesn't react with ketones, doesn't react with alcohols because it's a mild oxidizing agent, not strong enough to oxidize an alcohol, only strong enough to oxidize an aldehyde to a carboxylic acid. The sodium hydrogen carbonate, or you could use sodium carbonate, is used to test for the presence of a carboxylic acid functional group, because any acid, and that includes carboxylic acids, any acids will react with a metal carbonate to produce carbon dioxide. So therefore we'd be looking to see effervescence there. The acidified potassium dichromate, I think most people are happy with the fact that this is used to test for the presence of primary or secondary alcohols. Tertiary, no, we wouldn't get oxidation of a tertiary, but because acidified potassium dichromate is also acting as an oxidizing agent, we would also get a positive result with an aldehyde. We obviously tend to use Tollens. It's a mild oxidizing agent, it does the job, it shows us whether we've got an aldehyde or a ketone, and from there we can think about what alcohol we might have started with if we're trying to identify, was it primary, was it secondary, was it tertiary, and so on. But we can also use acidified potassium dichromate to identify an aldehyde, because it will oxidize the aldehyde to a carboxylic acid, as well as oxidizing our primary and secondary alcohols. So that is the bit that students tend to either not know or forget, that we can use that for an aldehyde. So now that we've done that, again, we can then have a look at the organic compounds, and again, we might want to identify what functional groups we have. So propan-1-ol is an alcohol, propanal is an aldehyde, propanone is a ketone, and propanoic acid is a carboxylic acid, and I've got their functional groups there just to make life potentially a little bit easier. Wouldn't have to do that, of course. These are all just ideas of things that may help. So if we then have a look at the sodium hydrogen carbonate column to start with, that would be us seeing effervescence for a reaction between sodium hydrogen carbonate with a carboxylic acid. Now there's only one carboxylic acid out of our 4 options, which is propanoic acid, which is D. So we would expect to see effervescence with propanoic acid. We'd expect there to be no visible change with the ketone and no visible change for the aldehyde, but we would expect there to be no visible change with the alcohol as well. So that result is wrong. And because that result is wrong, we can immediately rule out A. That's not correct. So we can ignore A now. Moving on to the acidified potassium dichromate column, ignoring row A, this is where some students, as I say, will go wrong, because with the aldehyde, yes, we would expect to see the orange acidified potassium dichromate solution turn green, and some students would have crossed that box, but it can oxidize our aldehyde. We should get no visible change with propanone, and we should get no visible change with a carboxylic acid, because neither of those can be oxidized. So that wasn't very helpful as a column because we didn't rule anything out there. So it all comes down to our Tollens reagent. Again, no point in looking at A because we've already crossed that. So it's given us a silver mirror for all 3 options. Well, Tollens reagent will only give a silver mirror with an aldehyde. So tick that one. Definitely not going to get a silver mirror with a ketone or with a carboxylic acid, because neither of those, again, can be oxidized. So that rules out C and D, meaning that our answer here has to be B. Had we have not known that the orange solution turns green for testing for the aldehyde with the acidified potassium dichromate, then I'm not sure how you would have kind of finished off that answer other than by guessing. Always make an educated guess if you're not sure, and if you're certain it's not A, at least that gives you kind of fewer options to pick from, but please do always have a guess if you are not sure. But hopefully that clarifies why the answer is B. Hopefully that's a useful recap for those of you in year 13, and hopefully will prove useful for those of you in year 12 in the fullness of time. Thanks so much for watching, guys. Any questions, as always, please reach out via comment or email on any of my social media platforms. Thank you so much. Catch you soon.